Hi, welcome back to another stats video. In this one, we're looking at least squares linear regression. Let's get started. So least squares linear regression is a way where we take a set of data and we try to fit a line that kind of captures the main idea of what's going on in that data. All right? So it is a mathematical model that's helping us sort of predict the response variable based on knowing the explanatory variable. Okay, and we call this least squares linear regression. You'll see in a minute why. And the thing is, with a data set, there's not going to be a single line that goes through every point if it's real data, unless it's really a perfect formula or something like that. So we're looking for a line that sort of captures the main idea of a set of points, okay? And then we want to quantify how well that line actually captures the main idea of a set of data. So if you have, here's you can see a set of data, and we've got this line that's kind of going through them. What we've done is we've drawn these lines down from the point to the line. Those are called residuals. And the farther away a point is from the line, the bigger that residual. And in a least squares regression line, what we're trying to do is minimize the sum of the squares of those residuals. So I'm going to jump over to the applets here. If you look on the applets, they've got the data sets down here for chapter 10. The applet is correlation regression, and I posted in just kind of a data set here, and you can see there's kind of a linear trend of these points here, but it's not perfect. If you click this correlation coefficient, it tells you that the correlation is 0.9, so that's a fairly strong linear relationship in these in this set. What I can do, though, is I can click this Show Movable Line button. And you can see, well, this line doesn't really go through the data very well. And if I click this button that says Show Residuals, you can see that the residuals are really big. But if I do this, now I'm kind of shrinking. Of course, if I make some residuals smaller, other ones get bigger. I can make those small, but then these get big. If I make those small, then those get big. And so I'm trying to find the line that does the best job of shrinking these residuals down. And it's not just the residuals I care about. It's really, I want to take those residuals and square them. And that makes an area, and I want to add up those areas and see if my residual is way off, those squares get really big. But if I can find it just right, then those squares shrink down. And here you can see the sum of the squared errors, 646. If I move this point, now it's 700, 800. If I move it down, I can get it down to 620, 609, right? I can shrink it down pretty well. Now, if I click Show Regression Line, it actually finds the best line through those points, and then it gives me the equation. Okay, so that's how the applet is going to work for linear regression. Okay, so you can use the applet when you're doing these problems. Okay, now the equation it spits out is going to look like this. It's called the regression equation. It's y hat equals a plus bx. X is my explanatory variable, my explanatory variable here, and y is my response variable. And so each of these data points is a real measurement of x and y. But the regression line doesn't necessarily go through all the points, so that's why we call it y hat. It's the predicted value of y. It's not going to be correct because for a particular x, it's usually off. So the x value is measured, the y value is predicted, so we call that y hat. And then a is the y-intercept and b is the slope. So wherever it crosses here at x equals 0, that number will be the y-intercept, and then this line has a slope, rise over run, and that's the number b. Okay? For any particular x value, if you take y minus y hat, that's called the residual. So you take what the value actually is minus the predicted value. That length is the residual. And then the slope of that regression line, this number b right here, is the predicted change in response for every 1 unit change in explanatory variable. So the slope is saying if I go over one value in x, how many values do I go over in y in my regression line? So the slope and the correlation usually have the same sign. So if the slope is positive, then the correlation is positive. If the slope is negative, the correlation is negative. If the slope is 0, the correlation is 0. But the correlation and the slope are not the same number. The correlation, of course, is always between -1 and 1, and the slope could be, -500 or 2 or any number is possible depending on how steep the regression line is. The y-intercept tells you where it crosses the y-axis. Now, one note here: you don't want to do extrapolation if the data. Here's a set of data here. These times are between 30 and 80. Well, the x-axis would be over here at 0. That would be way outside your range of data. So that's called extrapolation if you, make predictions outside the range of data, but the y-intercept is where the line crosses the x-axis. Here's a little note on extrapolating, predicting the response variable outside the range of the explanatory variable. And here you can see the number of husbands went from 0 to 1 over 1 day. Well, in a month, you could extrapolate and assume she'd have, hundreds of husbands or something like that. So, and then the last idea I want to talk about is the coefficient of determination. It's called R squared. It is just the correlation squared. So if the correlation is 0.5, the R squared, the coefficient of determination, is 0.25. It's just 0.5 squared. And what the coefficient of determination would tell you is how much of the variation in y is explained by x. Okay? And so you can see over here, for this one, the correlation is 1. It's a perfect straight line. So if you knew the x value, you would know the y value with 100% accuracy. So that's saying 100% of the variation in y is explained by knowing what x is. When r is 1, r squared is 1. But if r is, say, 0.9, then only about 81% of the variation in y is explained by x. And this graph here, I think, is negative 0.75 correlation. So what would happen here is you'd be explaining about 56% of the variation in y by knowing x. So if you knew x, you would kind of have a sense of what the y values are, but you can see there's a lot of variation that's not accounted for by just knowing what x is. And of course, this should make sense. Any real value is determined by lots of things. It's not usually determined by just knowing one thing. If I knew what your height was, I wouldn't know exactly what your weight was, but if I knew what your height was, I might know something about what your weight was. And plotting heights and weights in a correlation graph might tell you roughly how much information about a person's weight is encoded by their height. And that's what the coefficient of determination says. Take your correlation, square it, and that will tell you what percentage of the variation in the response variable is accounted for by a linear relationship with the explanatory variable. Okay, so that's the main ideas of least squares linear regression. In the next video, we'll do an example and we'll put some data down and we'll see how to work out the problem for a particular example. So we'll see you in the next video.